Hi guys, what you see here is a Bertan model 205A-05R high voltage power supply, and this power supply is rated to go from 0 to 5000 volts, from 0 to 5 milliamps. And I recently got this from eBay. It's non-working, and the only reason I got it is because it was listed at a very cheap price, and so I thought, what the heck, I will try to repair it. And even if it can't repair it, it will be definitely worthwhile to take a look at what is inside. Now, the problem of this unit, according to the seller, is that one thing is that this knob is very stiff, and which actually after I got it, it became less stiff, but I suspect that's just some problem with the lubrication, so which is easily fixed. I'm not too concerned about it. However, the main problem of this unit is that it actually doesn't work. And I will show you right here. Basically, as soon as you turn it on, the meter on the voltage side would go all the way to the maximum, and no, there's no voltage output, as the seller correctly stated, and I did check it with my high voltage probe. And so regardless what setting this voltage setting is set at, and there's no voltage output and there's no movement in the meter. And if you turn to this current mode, and there's no current draw. So, and also I noticed there's no positive negative indication either, and that's probably just some, I'm actually not sure what that is, or whether or not that's a part of the issue that is causing this full-scale meter movement. But nevertheless, that's the state this unit is in. And so right now, I think what I'm going to do is I'm going to open it up and see what is inside, and we'll go from there. And before I open this up, I just want to show you guys the rear panel. And here you can see that's the high voltage output. I actually right now don't have the correct connector for this. So what I did was basically just stick my meter in, which is not ideal, but of course right now the issue is that it doesn't output any voltage, so that shouldn't be an issue. And as you can see here, this one actually does support both positive and negative output, and actually I did try either way, and there's no output. So these are the main driver transistors, and actually these are, I looked it up, these are Darlington transistors 2N6578. So two of these are driving the DC to DC converter inside to produce the high voltage output. And one of the possible failure mode, I suspect, would be that these transistors somehow were damaged. And if that's the case, actually that would be an easy fix, as we can just replace the transistors here and the unit would be back working again. But I don't know. We can find that out later after I open it up. And let's see, this unit, as you can see here, that was model number 26018, and the date was 89 38th week, so it was it's almost 30 years old. Anyway, so moving to the right here, we have this input programming monitor. So basically you can supply a analog voltage to control the output voltage, and also we have the local and remote. So right now we're correctly set to local as we are using the front panel. So there really isn't too much to it, and now let me open it up and we'll see what's inside. So I went ahead and removed the screws, and now let's see, we can just open it right up here. Oh, whoops, there's one more screw, sorry about that. So there's one more screw here, didn't see. Okay, so now we removed all the screws, and let's see what is inside. Aha! So it looks rather simple inside, and there's really not too much to it. Oh, by the way, And I'm not sure if you can see this bending here, and this is another problem of the unit. Is it seems either it's doing shipment or something happened that there's some extraordinary force from the outside of the case push this left panel inside, and that actually kind of pushed the transformer towards the power switch. But luckily, it's not touching yet, so I don't think this is going to be the problem, but we don't know yet. Anyway, here you can see that the condition, the construction is very simple. Basically, we have the power transformer, and there's the filter capacitor right here. We can actually later on, I'm going to do a close-up of everything, and we can see a little better. But and this is a power transformer, and we have the controller board. And this board does look a little bit complicated because this unit does support external programming input. But anyway, so then we have these two transistors here, and the polarity switching switches right here. And this in this unit, that's the this is actually pretty soft. So anyway, inside here, that's the potted DC to DC converter. So now, as I mentioned earlier, one of the possible failure mode is that these two transistors are blown. And if that's the case, that would be easy fix. Another possibility is something's wrong with this DC to DC converter. And if that's the case, probably we won't be able to fix it, as these, you can't really open these up. And finding a replacement unit will be next to impossible. So really, that's actually pretty much everything inside this unit. And now I'm going to remove the camera from the tripod and show you guys some details close up. So let's start from the side of the unit where the transformer is located. And the first thing you can see is that this construction is actually quite interesting. You can see these two Curtis indicators here. Actually, I'm not sure if you guys know what this is, but back in the days, these are routinely used to test, to see how long the instrument has been powered on. So this one has 2 units, and each one is I'm not sure if you can read it, but it's 10,000 hours. So right now, the mercury inside already points to 10,000 hours. So which means this thing has been powered on for at least that much time. Now, these things are typically used for servicing and the warranty type of situation, and they are not extremely accurate. But these are very cheap, and just needs a power supply. So that's actually one of the pretty popular things back then. But I'm not sure why they need 2 units. Perhaps they're so cheap that they use these as a redundant measure. Anyway, so this is not important for the functioning of our circuit. And what I see here is a bridge rectifier, and the interesting thing is they mounted it on the side panel for some heat sinking capability. And these would be the main, I would suspect this would be the main voltage that is powering the DC to DC converter. And actually, as you can see, if you follow this lead here, and that's the wire, it goes all the way back to the DC to DC converter right here. So, and in this unit, you can see a lot of the cables are just wired around the side and cable tied together. So, well, that's pretty popular back then, and that's one of the construction methods. But obviously, it does add some problem to servicing, because now you have to totally determine the problem based on the color of the wire, and you have to do a lot of continuity checks to make sure that you are actually testing the correct test points. And I'm not sure what this thing is. It's just hang here. But another thing I noticed is it uses a lot of this kind of single-sided sticky pads to stick components to a surface. And you can see one here, right here as well. So the construction is really crusty, and they're really, is kind of using some, kind of like a one-off constructions, like the things that we do, I do rather, in my lab experiments. One thing I would notice is, I'm not sure you can see, so these are the two LED indicators of the polarity, as I mentioned earlier. And if you look really closely, okay, let me zoom in a little bit. If you look really closely, okay, so here is some like insulating pad, and here is actually a transistor. It's right tucked there, glued onto the side, and presumably is driving these indicators. But anyway, that's not working, so that's an area I would have to look at later after getting the unit back to work. And then here, moving on the front panel, you have these voltage and current range switch, and this is our main meter. And here, that's the voltage range selector. And so not too much on the front panel. And here's our 10-turn 5K pot that that we later need to service the front dial. Okay, so let's see what is behind here. And there's some wires coming out of this this soft potting material. And this is where the main high voltage goes out. Okay, so one thing interesting looking at this board, right now I'm looking at this board, is that and the construction is okay. It's probably on par with a lot of other things manufactured back in the days, but one thing I don't like about it is that all these ICs, right, all these op-amps, are all soldered directly onto the board, which makes it very difficult to service. And so what I'm going to do is, at the very least, I'm going to kind of take these out and put sockets back in. So in case the issue that we're seeing is because of the one of the ICs are bad, then we can easily replace them. And also in the future, if somebody needs to replace one of the ICs, it would be much easier. And if you look at this, these are the two main plus minus 12 power supplies. The regulators, and these are just kind of hanging there. Okay, and well, there's nothing wrong with this. You're not supposed to, this is not designed to be moved around, and so I guess this construction is okay. But if you look more closely here, excuse me, you'll see that there's some transistors. Oh geez, this is really crusty here. And there's some hot glue, and glue down a 2N3904, and there's another transistor stuck behind this 7912C, so the negative 12 volts regulator. So wow, so the construction is not what I would associate with a name brand high voltage supply. So the first thing I want to do is obviously just check, without even checking the voltage or anything, is just to check if this two pass transistor, or not pass transistor, this two driving transistors are bad or not. And if that's the case, that should be a pretty easy, at least an easy fix. So let's take a look. So this is my so that looks okay. That's probably just reverse biased. So let's take a look here. Yeah, that's a diode drop, and that's also a diode drop. I think yeah. So that one is good, and the other one is a little bit hard to get to, but we will see here. That is supposed to be connected together. Hang on. So okay, then to reach. There. Yeah, so that is also good. So that's also good. So unfortunately, it doesn't seem that this is the problem. As if this is a problem, that would be much easier to fix. So far that those two transistors look okay. And now the next thing before I do anything crazy is I'm going to check if the voltages are correct, which I probably should have checked first, but the transistors, those are so easy to check to begin with. And so anyway, so let me hook up the power again, and we will check the voltages. By the way, a word of caution to for people who are trying to serve these kind of high voltage units at home by yourself, is that you need to be extremely careful, especially you have the case open like this. There are potential points where the high voltage is going to be at, and you need to be absolutely certain you know what you're doing in order to service that. And when I was in college, and one of my professors taught us, basically whenever you're troubleshooting a high voltage circuit, always put one hand behind your back and use only one hand to investigate. The reason for that is in the event something happened, right? So you accidentally touched a high voltage point, and you will not be forming a closed circuit loop through your body, through your heart, which is the most dangerous part of being electrocuted. So, and also, if both hands are in the front, you could accidentally touch something that both sides are high voltage, and you won't be able to release in a timely manner before you are executed. So, basically, what I'm trying to say is just make sure that you don't use both hands poking around in the units, and always good practice to only use one hand, and try to be careful when you power it up, and do make sure that you understand at least how the circuit operates before you start poking around. So anyway, so let's switch this to the voltage mode. This case is grounded, as I see a lot of the points, the grounding points here. So the case is grounded. So I just put one of my meter lead in here, and I'm going to turn it on. So this time I'm going to be very careful, because this whole thing is going to be live. And so as you see, the meter is all the way to here. So let's just test the output from the regulator. So again, I'm going to only use one hand. So let's see. So this is my positive regulator. Yep, I have 12.202. And this is my negative. Negative is, I think it's this, right? No, that's the input. So it's minus 12.11. So the voltage looks okay. And let's check the main voltage here. So the main voltage is across this capacitor, which let's check. It's 40 volts, which look reasonable. And let's check this DC to DC converter. Yeah, it's also 40 volts, which is exactly what I expected, because that's it seems that this particular bridge rectifier that is mounted on the side of the panel powers this DC to DC converter directly. So from the voltage standpoint, everything looked okay. And just gonna spot check a few supply voltages on the an op amp. Yeah, 12 volts and minus 12. So I mean, we can keep trying, but they look pretty decent. So let me try this. Minus 12. 12. Okay, so it's, I mean, at least from right now, what we can see is that the failure, number one, is not a power supply. I mean, at least not an obvious reason if it ended up to be power supply. And it's not this two transistors, because they are good transistors. And just for that, let's see if we have any and the reason they're not working is right now you can see here are the C, which is your the collector of the transistor, and you can see that they're all sitting at 40 volts. So basically the circuit is not oscillating, which actually could be a problem. So let us dig a little deeper to see why it's not oscillating. So what I did here is actually I did some probing off the camera, and I think I found something. I'll show you right here. If you look closely, you will see that this region, I wanted to see this capacitor. This capacitor is different than everything else, so I assume that this op amp is probably the oscillator here. And so I started probing around to see if there's any signal I can detect. And yes, there are. So if you look at the oscilloscope, I'm just going to show you the oscilloscope right now. And okay, so it's up there. And so if I probe the number 1 pin, which is the output. Okay, hang on, let me just get steady here. Oops. And you can see that we do get output. Okay, so. And this is pin 2 and pin 3. So at the very least, we know that the oscillator itself is working. Okay. And another problem of this unit is, I can't find any exact circuit diagram for this unit. Which is unfortunate, because otherwise it would be much easier to figure out the problem. But without the circuit diagram, it's still possible. It's just going to take a long time to try to figure out what the heck is going on. And I probably will have to take the board out later, and as I mentioned, resocket all the op amps and hopefully try to reverse engineering part of the circuit, and so that I can see what is going on. Anyway, so I actually poked a little more, and I found that to the input of this Cascode Amplifier, which is a CA3028A, if you can see here, so this 1 is on the side here. Actually, that's a 7. Sorry about that. So let me see here. So if I hook that to one of the input, and if you look at the scope, we do get a signal. Okay. So which means so now I started to understand the circuit a little better. It's basically this is somehow a buffer used to somehow drive the output. But that said, there's no output from this Cascode amplifier. So I think that's a 1, 2, 6, right? 6 is where it's 3. Can't remember which pin it is. But anyway, I just measured. There's no output. I think it's 6. Yeah, so there's no output. Okay. So so that makes me believe either something has to be wrong with this amplifier here. So I think the next step I'm going to do is having to take the board out of the unit and go from there. So here I took the board out, and actually it's quite easy. It just slides out from that socket. And as you can see here is that capacitor I mentioned earlier. And the output of this, I just started tracing that and randomly, and then I found it goes to this this Cascode Amplifier, CA whatever 0. Let's see, CA3028A. Okay. So, but unfortunately, it doesn't have any output. Now, I don't know what the reason is, whether or not this is bad or there's some other underlying reasons. Because remember, the triangular waveform generated this has to go through a comparator somewhere to generate the correct pulse width to drive the actual high voltage circuit, so that you can control the actual output of the high voltage. You know, if you look at the so here is the bodge that I mentioned to you earlier, and you can see here this is the transistor glued, and there's another transistor glued on the back. So it's quite interesting, and there's a like hot glue everywhere, and there's hot glue here, but the back of the circuit looks rather clean. And unfortunately for this kind of older board, really, somebody is going to town. I mean, somebody had a great time trying to, like trace everything. So you can see that's winding around. Some of the traces are kind of obscure, but what you can deduce is that this outer region is definitely the ground, and there's some signals going in. So we can reasonably, trace it out a little bit, and see what it's doing here. So I went ahead and did a little bit of reverse engineering, and this is by no means a complete circuit here. And as you can see, there are a lot of the parts that are not connected. And so, but what I want to show you is this IC104A. That's the oscillator I mentioned earlier. As you can see, that corresponds to the circuit here. That's a C1. That's this capacitor here. And so that's exactly what this is supposed to do. And then that goes to the Cascode Amplifier. And for that, I actually drew the internal circuit out, because it's rather simple. I try to understand what it's doing here. And so it seems that this is actually only an intermediate stage. If I trace the signal after it's coming out from this Cascode amplifier, it goes to these two ICs that drives the actual output. So this 6 and 7, these are the pins on the edge board, and so these are the output to the base of the power transistors. And if you look at that IC106 is where is it? IC106, 104, 10. I think it's one of these. 106. Yep. So that's right here. Okay. So this one goes driving the output of the signal. So anyway, so I'm gonna socket this ICs, and we'll go from there. So I went ahead and socketed all the ICs, as you can see here, and all these, if you recall, were originally soldered directly, including this TO3 device, which is a Cascode amplifier. And now I put socket on all these devices in case I need to swap them out. And unfortunately, I found out that in my further testing, and I didn't show it on video, is that this IC, the TL083 rather, sorry about that, TL083, this dual op amp, and this Cascode amplifier both failed. And quick look on eBay, unfortunately these devices are had long become obsolete, and they are actually extremely pricey, surprisingly. For this one, you can get one for like $10, and for this TL083, And actually, surprisingly, you can't really find that many suppliers. And the only ones I can find are you can buy from China, but I don't know. I don't even know if those are the genuine TL083s. Anyway, fortunately for the TL083, we can easily use two of the TL081s. Like kind of to glue together, serve as a single TL083. So that's exactly what I did here. And so these two basically are the two single op amps, and I just kind of created this rather crude adapter board. And so this goes into the 14 pin that originally this IC was supposed to go. So I can plug in right like this right here. That, by the way, that was just for testing purpose, and also for this Cascode amplifier. If you recall, last time I showed you this the circuit diagram, which I deliberately draw out the Cascode amplifier. So you can see it's rather simple. Of course, for a very for this integrated circuit, these two transistors has to be matched exactly in order for the performance. But of course, for me, I just want to test to see whether the whole thing works or not. So what I ended up with is this rather crude construction of this Cascode amplifier. And obviously, even though these two back-to-back transistors are pretty well matched, of course, the performance will be nowhere near this originally IC, but I suspect it will still probably work, just not as well. So, by the way, so that's another thing I had to do. So basically, I'm using this in place of the original Cascode amplifier. Well, folks, I'm afraid some bad news. Remember last time when I mentioned that one of the faulty mode, besides the controller board and the transistors, it could be the potted inverter circuit. In fact, that's exactly what was going on. And unfortunately, I didn't tape the whole thing, but I can kind of give you a little bit rundown of what I discovered. So after I resocketed the boards, and I put this Cascade amplifier on, and I put this ad hoc TL083 made of two TL081s. After I put it on the board, everything seemed to be working fine. But as soon as I turn on the power of that power supply, the pass transistors get extremely hot, and so if you recall last time, actually there was some oscillation. You can see that on the input of these into this op amp, into this Cascode amplifier. So we know that the this oscillator board at least is working. But after I turned on the power, then I realized that the transistor is getting really hot, and I could actually measure the output voltage, but it was really low. So I turned off the power immediately, and then did a couple of other checks, and came to the conclusion that something is horribly wrong with this with the potted high voltage portion of the circuit. So anyway, since that was bad, and there really isn't anything I could do about it, so I ended up taking it apart, just trying to see what it was inside, and further analyze where the fault might be. So anyhow, I actually took this apart gradually. It's a little bit difficult, but with a little knife and patience, just little by little, I can kind of chip away this silicone type of potting material compound. Anyway, it's extremely difficult to take everything out without damaging part of the circuit, but I managed to relatively intact removing everything from this potted part. So as we can see, actually we have two of these high voltage capacitors rated 6,000 volts and 0.1 microfarad. This is sprig type of this capacitor. And we also have a few smaller capacitors, which I will show you later, and a couple of high voltage resistors. This one is actually only 18K, and this is about 430 ohm. And then we have our transformer core, which is the ferrite core. And what you can see here is that basically on one side, actually everything is on one side here, and so this is the inner core, and this is the outer core. So there's a big air gap in between, and it's quite common for these kind of high voltage transformers to have an air gap. And the reason for that is to prevent the saturation of the magnetic field, so that in the case of a short on the secondary, the current is limited and you don't draw too much of a current. So the primary, actually I took it apart, but the primary had about 20-30 turns on it, and so this is secondary. As you can see that the wire is rather thin, so there are probably a couple thousand turns here for the secondary. Anyway, so what I found interesting is that actually I can tell you that this capacitor is actually shorted. Well, not shorted, but it's not totally shorted, but however it's compromised for the rated voltage. And how did I find out that? Well, I found out that by just by putting it into a known high voltage circuit, and what I found is that there's significant current flowing through this capacitor, which explained why the transistors were very hot once I fixed the controller board. So let me demonstrate that to you, and so you will see what I'm trying to explain here. So how do I know that the capacitor was bad? Actually, typically for this kind of high voltage capacitors, the failure mode can be very subtle. So for example, here I can show you that I have my, bear with me. So if I use this multimeter to measure that capacitor, right? Okay, so here is, let me just put it on. So here is in the capacitor mode, and if I'm using this multimeter to measure it, okay, so you can see, let me just make sure you can see it. Okay, so, and it measures to be 169, 170 nanofarads. It's a little bit on the high side, but nevertheless, it seems to be working here. Well, actually, so that's a kind of a trap. A lot of people don't realize that for these kind of high voltage capacitors, the only good way to measure it is to put it under test under a certain high voltage to see whether or not there's any stress inside that caused it to discharge. And so that's actually exactly what happened to this capacitor. What happened is that, see, right now it looks as if everything is normal, but when it was under high voltage, actually the inside is shorted. So that caused the secondary of the inverter of the transformer to overload, and that's why the whole circuit didn't work. But to demonstrate that, I just used the components I salvaged from this high voltage transformer, and I built something on this breadboard, not breadboard, on this. I'll show you here. By the way, it's not plugged in yet. So on this Proto Board. So basically, you can see there's a huge gap here, here, and here. That's because of the high voltage involved. And so these high voltage diodes, I just used two in parallel, and nothing fancy. And these are the bleed resistors. Each one is 3 mega ohm. So I have enough that so that if I disconnect this from the power supply, the voltage will discharge in about 5 seconds. So anyway, so I paralleled two of the capacitors from within the unit here, and this particular transformer is from a buck zapper. So when I plug this in, this one outputs roughly 3,000 volts. After it's rectified and filtered, the voltage would be around 4,300, 4,400, depends on the actual voltage of the AC input. And so what I'm going to test here is first I'm going to measure the voltage output right here, and with just the known good capacitors here. So after this, I'm going to test the same circuit, and by paralleling this capacitor to with this good capacitor. And if this is any short in this capacitor, and I would notice a lot of I would notice an output voltage drop. So that's exactly what we're going to see. So let me hook it up, and we'll take a look at what we find out. Before I do everything, I just want to make sure that I clip everything correctly, so that I don't accidentally touch anything that is high voltage. And as I mentioned last time, you should be very careful when dealing with high voltage stuff. And if you don't necessarily need to, if you're not familiar with high voltage and don't feel comfortable about doing so, I would recommend you stay away from it. Otherwise, it could be lethal. Okay, so here I have this high voltage probe. It's a 1 to 1000, the range right now is. So I set it to 20 volt DC. I'm expecting to see somewhere like 4 or somewhere around 4 volts, just above 4 volts. So I just plugged in. You can hear the humming of the transformer, and I'm just trying to set it out of the way so you can read what the meter says. Okay, so you will notice as I started approaching this positive side, you'll hear it started discharge. You'll hear it discharging slightly. You heard that? So that's actually normal, because that's the contact of that probe. So right now we're reading about 4,360 roughly, where that in that neighborhood, the voltage. Now I'm gonna disconnect the high voltage and put that capacitor in question in parallel and see what we read. So now I first disconnect, and as I mentioned earlier, it takes about 5 seconds for this to discharge. So in the meantime, I'm gonna hook up just use some alligator clips so that I can actually place onto this capacitor here. So let me move this a little bit so that everything will be out of the way. And now I'm gonna plug in this power supply again, and this time, because I know it's a short, so I wanted to make sure that I don't put it in for too long. Otherwise, you're gonna put too much stress on the transformer and the diode. Anyway, so now I put it in, so you can hear that the transformer. Oh, actually, sorry. So that's where if I read here, you see it's only like a 0.3, 0.4 volts, which means it's only about 300 volts, the secondary. So clearly something is wrong with that capacitor. So with that said, all our diagnostic steps we took were actually the correct steps. And unfortunately, we were not able to fix this unit because of this bad capacitor inside this potted unit. Okay, folks. So originally, I wanted this one to be a repair video, but as it turned out that there are multiple parts that have failed in this power supply, and it's beyond economical repair. Of course, we can still repair it if we have the right high voltage module and a couple of the ICs that happen to be very hard to find and very expensive. If we do have those, we can easily fix this module. But for a unit that costs only, I don't know, $30, $40 on eBay, and really there is no need to continue doing that, unless, of course, I find the right components. Nevertheless, we, it's still a pretty good buy, as we have this very nice multi-turn potentiometer and a couple of nice switches, and a couple of nice transistors behind, and heatsink, so forth. So, and actually, I'm not sure if you noticed here or not. I actually, in the meantime, last time, if you recall, when the unit first came, has a dented side, and I actually went ahead and fixed that, but unfortunately, weren't able to bring the rest of the unit back into service. But hopefully you found this video interesting, and you hopefully you find that the process of trying to diagnose what went wrong at each step of the way, and we enjoyed the teardown of what is inside this high voltage unit. If you find the video interesting, please give it a big thumbs up, and I will catch up with you next time.